Okay, so for this part of the video, we are going to be using a dimensional matrix. So we're going to set out our dimensional matrix right here. And we're going to be doing this for these 6 terms, which is our pressure change, length, diameter, density, viscosity, and velocity. So we're going to just write out this matrix like so. And the variables that we want, or not the variables, the units that we're making this matrix for is kilograms, meters, and seconds. So we can start off, we know that pressure is going to be a kilogram on the numerator, so I'm going to give it a 1 since it's on the numerator, and there's only one. It's just a kilogram, not a kilogram squared. Then it's going to be meters on the bottom, and seconds squared. So I'll give it a 2, a -2 since it's on the denominator. Then for length, we know there's no units of kilograms or seconds, it's just meters. Same thing with diameter. And for density, this is going to be kilograms per meter cubed. So that's a 3 on the denominator, -3 since it's on the denominator. And then no units of seconds. And then for viscosity, we have kilogram per meter second. So a meter and a second on the bottom, and then our kilograms on the top. And then we know velocity is just meters per second, so no units of kilograms, so it will be 1 and -1 there.
Okay, so for this next step, we are going to be coding our matrix and trying to find the rank of it. So I actually have a matrix that we just found there, a piece of paper just to go off of. So let's just begin. So first we want to import a NumPy. And that's good. And now we're going to begin putting our variables in. Since that will, all of our matrices are based off these units. That's just a clarification there. So now I'm going to begin putting my variables in. So first we have pressure. I'm just going to say is uppercase P, or delta P is just going to be a P. And that matrix is 1, -1, -1, -2. Then we have length, which we know the units are just meters. Same thing for the next we have our rho, which is our density. Density will be 1, 3, and 0. Now we have viscosity, which I'm going to say is mu. And finally, we have velocity. Okay, so that should be all of our variables. And now I'm going to actually define our matrix. Just going to call it dimensional matrix, and that will be np dot C. We actually have to create the matrix, and then plug in all of our variables. So first we have pressure, then length, diameter, rho, mu, and v. And we also want to make sure that this is, the type is actually float. So we're defining our matrix as a float point. Okay, so that was fine. Now we're going to actually solve the matrix for its rank. So we'll do mp dot your algebra dot matrix. That will be for our rank, since that's what we're looking for right now. And then all I have to do is just put our matrix in, just defined. And it shows that our rank for this matrix is 3. So that means that we're going to have 3 different equations for our dimensional analysis. Okay, so now that we have our rank, we can actually start getting our dimensionless groups. So what we want to do is we have these 3 equations here. I'll show the screens. But what we have is we have some core variables, which we are going to use L, rho, and V, so length, density, and velocity as our core variables. And we're going to be finding the exponent for which each equation will have, each dimensionless group will have. So that will be for each of our non-core variables, which is going to be our diameter, our viscosity, and our pressure. So I'm just going to get right into it and start coding for this. So we want our matrix solver, matrix solver, and then we want to actually put in a new matrix for these 3 core variables that we have. So it's going to be length, rho, and V, and we want to make sure that's as type float. Okay, then we want a comma. What are we doing next? We need to put in our non-core variable, which will be our first non-core variable, which I'm going to just do D first. And then that will be also as type float. Okay, so now that we have all that, we can actually run this, and it should solve for the exponents of our core variable in our first dimensionless group. So there we go. So we can see that there's a -1 here at the start. So -1 for our length, then 0 and 0. So that means for our first equation, it's going to look like this. Either, since we're doing this one for diameter, we will have an equation that's either D over L or L over D. It really doesn't matter. Those are both dimensionless. And this is expected since we know that both of those variables they only have units of meters. So it'll be a meter over a meter, which will cancel out. So the next part of this is pretty easy. We just need to do the same thing. So I'm just going to copy the same code over and change up my my variables. So this will be for mu. So now we run that, and we can see -1, -1, -1. So we now know that our next equation is going to be our viscosity over all of these, all of our core variables. So length, density, and velocity. And sorry, length, not density. Length, yes, density, sorry. Yes, length, density, and velocity will be on our denominator for that. So it'll be mu over L times rho times V. And same thing with this one. It can it can also be, oh, sorry, there we go. It can also be the same thing with the numerator and denominator switched, since that's still dimensionless. Okay, so now we're just going to do the same exact thing for our last non-core variable, which is it's our pressure. Okay, so we get 0, -1, -2. So we know this last equation is going to be our pressure over no length, since it's 0. And then our density is just raised to the -1 power, so it'll be on the denominator. And then our velocity, we can see, is going to be squared. So it will be pressure over density times velocity squared. So those are going to be our 3 dimensionless group equations.
Okay, so for this next part, we want to be using the 3 equations that we found for these dimensionless groups to find Reynolds number. So we can basically rearrange our numerators and denominators around as many times as we want to, and it will still be a dimensionless group. That's exactly what the definition would be for a dimensionless group. So let's just write down Reynolds number first of all. So it's rho VD over mu. So looking at our dimensionless groups that we have, we can see that if we put pi 1 over pi 2, we'll have D over L over mu rho V and L. So now we can see that our lengths are going to cancel out and we get exactly what we want to. It's going to be D, and then this rho and V will come to the numerator. So D rho V over mu. So we can see that's exactly the same as Reynolds number. So that's what we got. For this next part, we are going to be looking at our Bernoulli's equation and also our frictional heating equation. And we're going to be manipulating them a little bit to show that these actually have a relationship with our dimensionless groups that we actually just found. So let me just write down some of the groups that we actually have. Well, actually, first I want to note that this delta Z is going to equal 0, since that's our change in height, and there's no change in height in this scenario in our cylinder. So yeah, next I'm gonna just write down our dimensionless groups, which we have L over D as one, and we also have, these are the only 2 that are going to be relevant for this problem. So we have delta P over rho V squared as well. So these are 2 dimensionless groups. Now we want to actually set these 2 equations equal to each other. So what we have is a negative F over here. So we know that this delta P over rho is going to equal negative 4F, which is our friction factor, times L over D times V squared over 2. So we can already see a little bit of our frictionless, or of our dimensionless groups already in this problem, but we can manipulate it a little bit more to see that. So first we have L over D here. We already have a dimensionless group there, so we're going to keep that. This 4 over 2 is going to cancel. And then we can move the V squared. Just take 1 over V squared on both sides. And we see that we just created another dimensionless group on the other side of the equation. So that's really going to be the relationship that we have between our Bernoulli's equation and our frictional heating equation, excuse me. It's really a relationship based on our friction factor.